can be covered up to this one. Just a minute. Okay, so this is the VA characteristic of a diode. Okay. See, resistance VA characteristics. See, this is voltage, and why is current on the y-axis, not on the x-axis? Any idea? இது வந்து independent variable, more like an input. Okay, so y-axis like a output. So voltage source நம்ம control இருக்கும். You have voltage source in the lab, not current source in general. Okay, so usually I is on the y-axis. So resistance on the, I can have a graph like this. அதே மாதிரி diode, if you have to give a VA characteristics, so this one, nothing to notice is the forward voltage is in volts, reverse also in volts, but the current, the forward direction is milliamps, but the reverse direction it's micro. Okay. So last time I stopped with rectification because this diode, in the forward direction the current is high, milliamps. So in the reverse direction the current is microamps. So when it is reverse biased, it's almost like zero current if it's ideal diode. Okay, so but even if it's a normal diode, the reverse current is very small, so we can almost say it's zero current. So here inga vandu this AC input, it will be like this. Okay, so for this potential, for these values, it will be positive. Depends on the winding. Assume the winding is done such that when this is positive, this is also positive. Okay, so for one half, this will be positive, this will be negative. So that time this will be forward biased. Upon the almost zero resistance, so full current will come here. Okay, so if there is the AC voltage here, the corresponding current will be AC current, and the corresponding voltage drop will be AC. So then the positive half light, it's happening here. For this negative half, this input voltage, this thing is negative, this thing is positive. So it's reverse biased. So the current here is almost zero. It's like a open switch. So this current is very, very small. So this voltage drop is also very, very small. It's almost zero. Okay, yeah. So the same thing will repeat for the next cycle. So when the input is full sine wave, the output is just only the positive halves. Okay, so this is rectifier in the sense the direction is only one direction, positive direction. The current is flowing only downwards, not in the opposite direction. The same thing, same way I'll extend here. So when this is positive, this is plus, this is minus. So I can have a situation when this is plus, this is 0 volts, and this is negative volts, because I'm touching the center point and making it 0. So you do the maximum difference 230, this will be 115, this will be minus 115. So this will be forward biased, and this will be reverse biased during the positive cycle. So current will come in this path and will come here and flow here. This path, this is like open switch with this reverse bias. So here the current will be 0, almost 0. So here with the full current, whatever is coming here. So the drop here will be from here to here. Again, the current is flowing in this direction. When this thing becomes negative, second half of the input, for this one, this will be minus, this will be plus. So this will be minus, this will be plus, and this will be 0. So this will be reverse biased, and this will be forward biased. So the current will flow in this direction. This is plus, the current will come here, go like this, and again it will go downwards only, because you have done the connection like that. Okay. So that's why the output is always positive half. Even the input is negative, this thing will push the current from A to B. But the path is via D2. Here the D1 is conducting, here D2 is conducting, or D2 is on, but the current direction is always from A to B. The connection is made such that it's always A to B. That's why we are getting the current for the second half also. So this is full wave. I mean, in the sense the current is flowing for the full input. So this is called full wave rectifier. Okay.
Okay.
So this circuit you have to remember, and this diagram you have to remember. And so in this semiconductor, this is the reverse bias situation where the depletion width has increased, because the positive terminal is connected here. This will repel the holes to move this way. So if this has got P type, so there will be holes here. So when the hole moves, this will be negative ions. And this positive will attract the electrons. So the electrons will come here. So this will be positive ions. So without bias, in 0 volt supply, only 2 layers are visible because of the diffusion, positive and negative. But when you apply forward bias, so this holes will get pushed towards the junction. So it will be just 1 layer. So the depletion width is decreasing when it's forward biased compared to 0 bias, no bias. In the reverse bias, it's opposite. The depletion width will increase. So here it's difficult for the charge to cross this region. So if you take electron, here it's supposed to get attracted, but here it's negative, and this amount of negative repulsion is huge. So the barrier here for the electron is this big. Here this valley, it will get attracted. From here to it's no problem. But this barrier, only the electron is getting pushed by a higher energy, it will cross. So that crossing is very small, because the voltage is not that high. But here, the barrier will be reduced, because the thing is reduced. So it will be like this. So with a little bit of voltage, this will cross. Here will be in between. So here you can see medium height. This is small height. This is large height. Okay, so that is difficult for the electron to cross. Similarly, the hole to cross this means it will be difficult to cross this part. So the barrier will be opposite. For hole, you have to draw like this, because it's positive charge, right? So you'll get repelled from this positive ions. You'll get attracted with this negative. So this is not a problem. But this part, again, the same amount of barrier it has to cross. So it's difficult for the holes to cross this region. So, but if this thing is, if you apply more and more voltage, the field here becomes stronger and stronger. There is an electric field here. Okay, if it becomes very strong, you will start breaking the bonds here. Because the charge here is increasing, because reverse bias, this charge is more, plus Q and minus Q. Compared to forward bias is minimum, no bias it has some value. So in reverse bias, the charge is maximum. So the electric field in this depletion region will be maximum in this reverse bias condition. So if more are exposed, you apply higher voltage here. When the electric field becomes strong enough for this to break the covalent bonds here. Silicon will have 4 covalent bonds. In addition to that, there will be free electrons if it is phosphorus, or it will be free holes if it is boron, the impurity which is added to the silicon. This silicon here, and there will be impurities in between. So for this free electrons and holes to move, this voltage is enough. But if this electric field is strong enough, it will actually break these covalent bonds and produce free electrons and holes. So there is two ways in which it can happen. One is called avalanche breakdown, in which the material is lightly doped. This P and N for this P out add phosphorus impurity. For this inside out add, sorry, P out inside out of phosphorus impurity. For this P side out add boron as impurity to create this extra holes. Okay, but the amount of boron, if I add more, means doping is high. Then I have number of holes will be more. I can increase the number of holes. Similarly, if I add more impurity, that's heavily doped, means the number of free electrons are will be more. But in the case of lightly doped junction, the depletion region will be wider, because only if I expose a large region of depletion region, this or I can put this. For the same if whatever 3 volts applied here, if it is lightly doped, means large number of layers have to be exposed for the holes to come. If it is strongly doped, means only a few amount of this thing will produce that much amount of holes. So if it is lightly doped, means for the same voltage, the width of the depletion region will be large.
Okay.
So reverse way is okay. Wide depletion region, and this charge carriers will collide with semiconductor, breaking the covalent bonds because the electric field is high. This will produce electron hole pairs, which will start conduct. Another meaning of avalanche is like the general meaning of avalanche is, suppose this is a mountain, there is a snow here. When it rolls down, it will become more and more snow. The size of the snowball will increase. So this is called avalanche.
Okay.
Only here, when the breakdown happens, it will break few covalent bonds, and that there will be more electron holes will break further bonds. Suppose this one electron will break the covalent bond and produce 2 electrons. So that 2 will hit 2 more and produce 4. So it's like a chain reaction. Similar nuclear reaction, uncontrolled nuclear reaction, where it goes in geometric progression. So here also, that new electrons will collide and create more electrons and holes. So which will increase the current. So more collisions leads to avalanche. Avalanche is controlled large number. It's like uncontrolled nuclear reaction, where 1 neutron will produce 3 neutrons, and that 3 neutrons will produce 9 neutrons, right? Or 27, something like that, geometric progression. Similarly here, 1 electron, when it collides, will break a bond and it'll have 2 electrons. The 2 electrons will collide with 2 more to produce 4. 4 will collide with 4 more and produce 8. So this will keep on, and there will be a large current. So this is breakdown. Similarly, there is another way of having this doping. If the thing is heavily doped, the depletion region will be narrow, because a narrow layer will produce large number of holes to overcome this voltage. So here, electric field is potential difference due to the distance, right? So if the thing is narrow, okay, since for the same voltage, this is D is going down, so electric field will increase. So the electric field for a sheet charge, it is sigma by epsilon naught, right? This you have studied? Okay, so in this avalanche breakdown, the amount of charge is more. Q is high, so sigma is high, so electric field is high. In Zener breakdown, charge is there, but the distance is small. So you can also think electric field as V by D, where distance is small, so the electric field will be very strong. That will break the bonds.
Okay.
So here also the chain reaction will happen. So there will be a background. This is called Zener effect because this thing was first discovered by Zener. So this breakdown is called Zener breakdown. The difference between the two breakdowns is the doping. So here the depletion with this narrow, here it will be large.
Hmm.
So Zener diode uses this Zener breakdown mechanism. So Zener diode is same PN junction, but the doping is high.
Okay.
And the normal diode symbol is straight, but Zener diode is like a Z.
Hmm. Okay.
So this was similar to the diode, but in the normal diode we only use up to here. But in the Zener diode, in the breakdown region, the interesting thing is the voltage is approximately constant. It varies in this narrow band, but the current is changing by a large amount.
Hmm.
Okay, so it can absorb huge amount of current without changing the voltage. That will be clear if you see this
Okay.
circuit here. So there is a input voltage source, some series resistance to protect this one, and there is a load resistance here, and we connect this one. Suppose by mistake this V has increased by a large amount. In that case, suppose this thing was not there, large amount of current will flow here, which will damage this one because there is a heating effect, right? I square R. So if it is beyond a certain value, this thing will melt. This could be any appliance, whatever appliance you have in your home. To protect this one, when this current is increasing, because of this increase in the voltage, suppose this thing absorbs large amount of current, then this current will be reduced.
Hmm.
Then this voltage will be stabilized. Okay, so this voltage, the voltage across these 2 points, the maximum value is Vz. That's the breakdown, this voltage. Beyond this, the voltage will not increase. It will increase only slightly, but it's
Hmm.
almost constant. So Vz.
Uh,
So if this input voltage increases by some mistake, it will try to produce large amount of current, but if this current flows here, the voltage here will increase, but that will not happen because if this tries to increase here, large amount of current will flow here. So
uh,
this thing will absorb huge amount of currents without increasing the voltage much. So this thing will get protected. So this is like
uh,
a AC supply of your house. This is like a voltage stabilizer, and this is a fridge. Okay. So this sort of a mechanism will protect the appliance from voltage fluctuations. So this is basically voltage stabilizer or voltage regulator.
hmm. Okay.
Application, voltage regulator, fixed reference voltage, protecting the gadget against damage. Okay. So you have to make sure that this positive terminal of the supply is connected to the negative of this Zener drive. Okay. But
Okay.
if this is AC means when it's positive cycle, this will be reverse biased. So what you have to do is you have to connect one more here like this. Okay. So to reach the negative half, large amount of currents can flow here. It's not in your book, but just I'm saying for the sake of completeness.
Um,
Okay.
uh,
Because AC segments will be positive and negative. During positive, this thing will absorb the current. But it's negative, this will be
uh,
forward biased. So if I connect one more thing in parallel with the opposite polarity, then this thing will
uh,
take the current when it is negative during the negative cycle.
okay.
So here the thing is 9 volts. So the maximum voltage across this thing will be 9, approximately 9. So the current here, I can fix it. I mean, in the sense it's fixed. There will be 9 volts by 2K, that is 4.5 milliamps. Okay, and
Okay.
4.5 milliamps. So this current is, if you assume this is 0, this plus 50, this voltage is 15 volts, and this voltage is 9 volts. So the drop from here to here is 6 volts. So this current is 6 by 1, that is 6 milliamps. So 4.5 milliamps is flowing here. So the remaining this thing, 1.5 milliamps will flow in the zener diode.
Uh,
Okay. So suppose by mistake this thing becomes 16, this thing will still be 9, approximately 9. This current is fixed. It's 9 by 2.5. So the extra current will flow here. So that this thing is protected. So this thing is always 4.5. Even if I make this 20, this will not change because this drop from here to here is 9, always 9.
uh,
Okay, so whatever is the extra current just observe will go through this one. And this current will increase correspondingly. When this current has increased, this current is this plus this. So this current will increase, this will increase, but this current will be same.
oh,
So optoelectronic devices, so from the name you can see, input is optical light and output is current or electrical energy. You can also other way around, input can be light and output is current. Okay, so light emitting, that obviously it's emitting, so output is light. Input is current or electrical energy. So symbol is this one, same PN junction, except then you have to add this 2 years. It's a light which is coming out. Okay, so light is coming out because some energy has to be lost. So this, there will be recombination, this P type, N type. So it will be, it's the electrons here, there will be holes here. So at the junction, there will be recombination. The electron will combine with this thing, and the electron will be in the conduction band, and hole is in the valence band. The movement of hole happens in the valence band, and the movement of electron happens in the conduction band. So energy of the electron in the conduction band is higher compared to the energy of the hole in the valence band. But these holes can move, but the electrons in the valence band cannot move. Electrons can move only if it is in the conduction band. But holes in the valence band can move, and holes will be in the, only in the valence band, not in the conduction band. But the energy of the holes in the valence band is less. So when electrons and hole combine, it will disappear, both will disappear. So that's why electron is jumping here, and it's both are getting destroyed. But there is a drop of energy. So this energy will come out as light. That is represented by the symbol here. So just the same PN diode, just pass current. When the current flows, continuous electrical energy is passing through this one, which is coming out as light. So this is east to indicated in all the devices. Because you want to know whether the device is on, just connect this LED in series with the device. So this is your fridge. Connect this LED with this fridge. So when the current is passing through the fridge, current is passing through this diode LED and will give out light. And if this switch is off, means current will not flow, so LED is off. So this is just an indicator in all devices, indicator lamps.
mm,
Even in household equipments. 7-segment display for calculator and all, even for display board. All numbers you can generate by this 7 segments. This 1, 2, 3, 4, 5, 6, and 7. One here, two here, two here, and the one in the middle. So 7 segments. So number 1 is, you can get like this. This is number 1. And number 2 is like this. So all numbers you can generate like from here. That you can figure out, right?
yes.
So this is number 1. And then Number 2 is this one. And 3 also you can get. Okay, so 0 to 9 you can get from this one. That's all the digits. So each one is one LED. So this wavelength of this light, since it should be visible, this thing, so the energy of this electron is what the difference should be such that the energy that's coming out, that's h nu, that nu should be in the visible range. That you should choose the semiconductor properly. So for example, this gallium arsenic phosphorus semiconductor. So gallium is the intrinsic semiconductor. No, all are this. Okay, it's a combination. And this energy gap is 1.875 electron volts. So does this kind of correspond to the visible light? That you have to figure out. So E equal to h nu, which is hc by lambda, mu is c by lambda. So from that, if you get lambda, h is a constant, this one, and c is also a constant. And this energy is 1.875 in electron volts. To convert into SI units, 1.6 10 to minus 19. So if you put that, you'll get 660 nanometers. That is in the visible region, which corresponds to. So we choose this LED material such that this gap between energy difference between the electron and hole is in the visible region. Okay. Is it clear?
No.
Photodiode is opposite. Input is light, output is current.
Okay.
Optical to electrical. That is the conversion. It's inverse of LED and photodiode. So this is the symbol. Light is the input, so it's light is falling inside, and current will flow in this device.
Okay.
So alarm system, like when there will be a light here. So if someone is walking here, he'll block the light. So once the light is blocked, the current will not flow. Once the current flows, something will get triggered. Solar cell, again the input is solar light instead of this normal light. The light will be from the sun, and the output will be current. Generates the energy. So these are the solar cells which is used for power generation. So it will be huge this thing. So light has to. So this is the junction. This is the N side, and this is P, and this is the junction, the depletion region. So light has to fall from one side. So here light is falling, and there has to be metal contact because PN junction diode. There has to be contact on both the sides, right? This is a PN. So current has to flow like this. So for that, there has to be metal contact here. And also light has to fall here. So that's why there is some gap in this contact here. One contact is full, but the top part where the light is falling, sunlight, there will be some gaps. Only this part is electrical contact. Here there is a gap, which is anti-reflexive coating because it should not reflect the light. Light has to go enter this part. That's its anti-reflective coating. So light will enter this one, and it will create electron hole pairs which will move and produce current. So sunlight is creating this charge carriers. Production of charge carriers will produce the current.
Okay.
So calculated without using the cell, this solar cell can be used. Even the normal tube light, it will work with that light. SAT is obviously in outer space. There is no other form of source of energy. It only works through energy from the sun. All the satellites. So the solar panel will be huge. This is one way of producing electricity because it's so to reach on again in 10 minutes. It will cut after 10 minutes.
Okay.
So this is for production of electricity. Large number of solar panels you have to use and produce the current.
Okay.
So now diode means we have just one P and N. One P type semiconductor an N-type semiconductor. So if you have the third block, which is same P, so this is PNP transistor. Similarly, I can also have N, P, N. This NPN transistor. So here there will be depletion region. There are two junctions. One junction is here, and the other junction is here. Okay, similarly here also there will be one junction here, one junction here. And we can connect external sources. So if you connect like this, see this is positive. So this junction will be forward biased. Because P is connected to positive, this one is connected here. But here P is connected, so this junction will be reverse biased.
Okay.
Similarly here I have to connect. Okay, I'll show in the text. So this is NPN transistor, okay, and where the current is NPN means the thing is majority carries electrons in the same region. So electrons will flow like this. Depends on the biasing. Okay, and the arrow mark is putting on the emitter. See, one of them is called emitter, the other one is called collector, and the middle one is called base. So emitter in the sense, it's emitter of the charge carriers. Collector is the one which is collecting the charge carriers, and base is in between them. And the arrow mark is put from P to N. So this one, once you see the arrow, you can straight away put this is P, and this is N. Obviously, this has to be N. So this is NPN transistor. Here the arrow mark is like this. So this is P, this is N, and this is P. So this is PNP transistor.
Okay.
Okay. So it's basically consists two diodes. So this is called emitter, base, and collector. And obviously, these things you can decide how much this thickness has to be. Okay, so by design, this thing is thin compared to emitter and collector is slightly bigger than the emitter. So this one, NPN transistor, so for that to be forward biased, this has to be negative voltage. This has to be positive voltage. Only then, one way to check for negative voltage. So once I connect this negative here, it will repel the electrons. So the depletion region will become thinner, right? So that is the condition for forward bias. So here, when the positive thing is connected here, more electrons will move towards this positive terminal. So the depletion region will be wider. So this is reverse bias.
Okay.
This thing is forward bias.
Okay.
So if I make this as 0 volts, okay, so compared to this will be some positive voltage. So this is 0 volts and this is positive volts. Sorry, negative 0. So this is forward bias because this negative thing will push the electrons. So the depletion region will become thinner, forward bias. So this is 0, this is positive voltage. So this will push this will attract the electrons here and will make this thing wider. So this is NPN transistor. And here, there are 3 terminals, right?
Yeah.
This is a transistor. There are 3 terminals, emitter, base, and collector. Okay, so I can give input here between these two because voltage will have to give between two terminals. So this is input and this thing is output between B and C. Another possibility is I can have emitter here. There are just three wires, so I can do whatever I want. So this is base and this collector. So input is here between these two, and this is output. Third possibility is collector is in the middle, and emitter is input, and sorry, base is input. Oh, I have to rejoin here. Input is base, output is emitter. See, when base is common, input is emitter, output is collector. You cannot switch it around. Okay, so in some sense, I will say base, it has tendency to be in the input. It won't be in the output side. You can check here. Base is the input only. It's not the output. Collector, it's in the output side only. At the maximum, it can be common. But emitter can be both input and output. Here it is input, here it is output. Okay. So this you have to remember. So this is called common base configuration, this common emitter and this common collector. So there is some bias between these terminals. Emitter can be both input and output. Collector, it prefers to be the output side, and base on the input side.
Okay.
So common base, obviously emitter should be in the input. Collector prefers to be in the output side only. And this is second is common emitter configuration. Common emitter. So this is the emitter terminal. This one. Emitter terminal is common. So input is between the base and the emitter. Output is between collector and emitter. Because base prefers to be in the input side, collector on the output side. Third possibility is collector is common. Base will be in the input side. Emitter can go anywhere. So emitter is in the output side.
Okay.
So what they have shown is NPN transistor. So first they have studied common base configuration in detail. See, these two junctions, so the first possibility, this is forward biased, this is reverse biased. Second possibility is both are reverse biased. Third thing is both are forward biased. Okay.
Okay.
So here the current will be minimum. So this is like off state. Here the current is maximum, so it's like on state. This is normal state. You can call it active state. So these things are possible by using a proper voltage between these two terminals.
Okay.
That's called biasing, applying suitable DC voltage across the terminals. So forward active, emitter based junction is forward bias, collector based reverse bias. This is called active mode and acts as amplified. Saturated means